All right, welcome back. A while ago we talked about electric fields for charged particles, and also for like in the electric field produced by the parallel plates. And today we're going to just go back to the topic of electric field, and I'm going to introduce you guys another way of actually calculating electric field based on different type of charges. Okay, and so in today's lecture, we'll talk about electric flux and then Gauss's law. Just keep in mind that for today's lecture, actually, there's not a chapter in the textbook that covers this. So it will be solely based on the lecture here for you guys to learn. All right, so first, let's take a look on the definition of electric flux. Okay, so electric flux, um, according to its name, is like how much electric field going through a certain area. Okay, so if you have an area like if you have a rectangular area and then electric field is going through it, so then to find the electric flux through this surface, you do electric field E, the strength of it, times the area of this rectangular shape, and then times cosine of the angle theta, which is the angle the electric field makes with the normal direction of the surface. Okay, so in this case, electric field is perpendicular to the surface, so normal is also perpendicular to the surface, so the angle theta will be 0. Cosine of 0, it's actually 1, so then it will be just equal to E times A. In another scenario here, if the surface and electric field are parallel to each other, then normal direction and E field will be perpendicular to each other. So the theta angle will be 90 degree, then cosine of 90 actually will be 0. So electric flux on this case will be actually equal to 0. Now in general, if your E field and the surface makes a direction, makes an angle, so then we'll be looking at the angle the normal of the surface makes with the electric field. So angle of theta. Okay, so in general, it's EA times cosine theta, but the angle theta is the angle between the electric field and the normal direction of the surface, not just the surface itself. Okay, so that's the definition for electric flux, is measure of electric field perpendicular to the surface in that sense. Okay, so in this case, you'll be just looking at the component that of the electric field that is perpendicular to the surface. So E of cosine theta. Okay, E of sine theta parallel to the surface will give you 0 flux. All right. Now we know for surface, so it has two normal direction, right? So if you have a surface, in the previous case, let's see here. So there's a front surface, that back surface, okay? So if we use the front surface here, then the angle is 0. But if we do the normal direction of the surface there, the angle will be 180, okay? So cosine of 0 and cosine 180, they're not exactly the same. So one will give you positive, the other one will give you negative. So then in that case, if we look at this, so we need to define which one to be positive, which one to be negative, okay? So the definition is the flux is positive if the field lines that leaves the enclosed surface, enclosed volume of the surface, okay? So normally you will not just have a single surface, you'll have a few surfaces or maybe an enclosed surface that it will be considering. If the flux will be negative for the field line that enters the enclosed surface. Okay, so let me give you an example of, let's say, if we have a cubic surface or something similar. Okay, so then here, on the cubic structure here, so if we have E field, let's say E field is going in maybe in this horizontal direction. Okay, so E field. So then when the E field enters this surface on the left-hand side, okay, it's entering the volume. Okay, so then electric field, electric flux through this one will be negative. Okay, on this side will be negative. Now electric flux through this right surface over here, then actually it's going to be positive. Okay, so that gives you a sense of which one to be positive, which one to be negative. Okay, so when we talk about the two surfaces there, or the two signs there. Okay, all right. So let's move on to the next one. Um, Now let's take a look on the electric flux by a point charge, a field produced by a point charge. Okay, so earlier we learned that for a point charge, the electric field is going away from the charge and in the radial direction in that case. Now, if we have a spherical surface here, with the center of the sphere and the location of charge. So then we know that for the electric field produced by this guy is equal to, so if you remember, for E field, E for a point charge is KQ on the point charge over R squared, okay? The surface, if this is spherical surface, for a spherical surface, okay, so then A is equal to 4 pi times R squared, okay? And the electric field, because it's pointing in the radial direction, so at any point on the surface, it's going to be just in the same direction as the normal direction, okay? So then if we are considering electric flux through this spherical sphere surface over here, then you can just do E times A. So E times A, you'll see E times A in this case will be this guy multiplied by this one, which is KQ squared times 4 pi R squared up there. So then the R squared and R squared will cancel. So then you'll end up with just Q over epsilon naught, okay? Where actually K is as a constant, which is 8.99 times 10 to the negative 19, or times 10 to the positive 9. And K is actually also this guy here, 1 over 4 pi times epsilon naught, okay? So if we rearrange the term here, then you get that epsilon naught is equal to 1 over 4 pi times K. So then 4 pi times K in here remain over here 4 pi times K here, then actually is equal to 1 over epsilon naught, okay? So at the end, the result should be just that Q over epsilon naught there. So that will be your just be your result there, okay? So that gives you that, okay? So we can see then flux, electric flux here is equal to, actually, is equal to this guy, E times A, and then at the end is also equal to that, okay? For a point charge. So then we can conclude that on the second way of solving for flux, it's going to be equal to Q over epsilon naught. Okay, so from maybe you can go back to the previous slides here, you can see electric flux on this surface over here, okay, is then equal to just that guy over there, okay? So it's just Q, the charge it encloses, this surface encloses, divided by a constant number epsilon naught, which is equal to this, okay? So that. So here's the conclusion. So you can also calculate flux by using the charge enclosed by a particular surface, not necessarily spherical. It could be any arbitrary surface like this. That would be also fine. It could be a cubic surface, or it could be a cylindrical type of surface, okay, like that. So the surface is actually arbitrary. Okay? It doesn't have to be a specific shape, but this law, this is called Gauss's law. So it says that the electric flux through a closed surface is proportional to the charge enclosed by the surface. Okay, so any type of surface. Okay, as long as it's enclosing a certain charge in it, so then flux will be equal to that. Okay, so this is Gauss's law. Gives you a second method of calculating flux, and we can actually combine that with the first the definition of the Gauss's law, which the flux, which says flux is equal to electric field times the surface. And then if the electric field is not perpendicular to the surface, you will include a cosine theta as well. Okay, and combine these two, you can see you can set up this Q over epsilon equal to EA. If there's a cosine theta, you will include that. Okay, and then you can calculate for the electric field. Okay, so we'll take a look on a couple of examples here today. So the first one we'll be looking at if we have a line charge here. So this line charge over here on the green line here, it says if you have an infinity line charge, which lambda is the charge distribution there. Okay, so maybe a few things here. So lambda usually is line charge. Okay, or line charge density in that case, linear density of charge. Okay, and sigma will be surface charge density. And then normal rho will be the volume charge density. Okay, so a few notations here that you guys will be seeing, lambda, sigma, and rho. Okay, so for line density. So here, lambda, that means line charge density. You have a line that have charging uniformly distributed through it. Okay, it's asking you what would be actually the E field produced by this wire at the radial direction R away. Okay, so somewhere there. And here, now because it's infinitely long, you can take a spherical or cylindrical surface here, or like draw a cylinder, its surface called cylindrical surface. Okay, so on the side here, cylindrical Gaussian surfaces, and then you have two bottom here and one on the other side. Okay, so that gives you an enclosed surface, cylindrical Gaussian surface over there. Now, E field, it's gonna to be, you can see if we have a charge on this side, right, a positive Q, a Q, just say a Q there, positive Q, and then in the middle there, the same distance away from that Q, we can take another Q because this is a uniformly charged, so you can have a charge on one side and then you'll find another charge on the other side of your symmetric axis. Okay, so let's say here, this is the axis. So now at any point over here, we will see that E field by this guy is going to be pointing in that direction. E field by that guy is going to be pointing in that direction. Okay, so this E field will have a horizontal component. This E field on the other side will also have a horizontal component. Now the same charge Q, the same distance R, so its horizontal component actually will be canceling out each other because they are pointing in the opposite directions. So the vertical direction is going to add up. Okay, so one here and one there is going to be adding up. So you can see electric field by such a line distribution of charge, infinity line distribution of charge, we'll just have electric field that's going away from the radial direction. Okay, so pointing away. And then at that location will be pointing away like that, and that particular location will be pointing away like that. Okay, so the electric field will be just in the radial direction. Now this is a little bit messy. I'm going to just clean out things before we actually take a look at the electric field. Okay, here. All right. So here we are enclosing this part of the line charge. Okay, just this part from here to there. Okay. So then E field is just going in the radial direction. Okay. So from two ways I'll calculate the flux. Phi flux equal to then E times A. Okay, there are three surfaces here. On the side surface here is E times A. At the bottom surface here, And on this other side there, because E field is in the radial direction, right? So then it's parallel to this. Okay, E field is in that direction, E field is in that direction, parallel, kind of parallel to that surface. Okay, because it's in the radial direction. So then by the two surfaces will be zero, and then another one will be zero as well. Okay, so E field that we are looking for in the radial direction times the surface of this cylindrical Gaussian side surface. Okay, cylindrical Gaussian surface should be equal to the circumference of the base times the length. Okay, so that should be 2 pi r circumference of the base times the length of L. Okay, it's equal to that. So this is according to definition. We are calculating the flux, electric flux through the side surface to the two bottom surface add up, okay, to be 0 and 0. And then that's the electric flux. Now, according to Gauss's law, flux should be also equal to just the Q enclosed, okay, enclosed over epsilon naught. So then Q enclosed will be just that little part over there, the length of L, and the density will be lambda. So then that will be just lambda times L for the charge over epsilon naught. Okay. So this is also flux. So these two then should be equal to each other. So we'll set up those two equal to each other. So then E times 2 pi R L then equals to lambda L over epsilon naught. Okay. So you can see that will be cancellation. L and L cancel out. Okay. So then you'll divide both sides by 2 pi R to get E. So E at the end should be equal to just lambda divided by 2 pi R times epsilon naught. Okay. So that will be your result. Let me see if I can write it a little bit better. Let me figure out that. So E is equal to lambda over 2 pi epsilon naught times R. Okay, that will be the electric field at the end. Okay, so you can see it's inverse proportional to R. As you are going further away from R, E will decrease. Okay, and that's the only variable there. Okay, all right. Next, let's take a look on surface charge distribution here. So Gauss's law, surface charge, again, sigma, as I mentioned earlier, so it'll be this sigma there, okay? So in this case, we can draw a cylindrical shape here of volume, and it will have a two bottom side, and then a side surface, cylindrical surface, okay? So again, you can use symmetric. So electric field on a sheet, uniform electric field on an infinity sheet here will be actually, again, just perpendicular to the sheet and then pointing away. Okay, so the same thing we can do. Maybe you can draw a center axis here through here. And then if you get a charge here, and then on the other side of this distribution, you get another charge, which is this is be equal distance away. Okay. And then at certain point of interest P over here, electric field by this guy is going to in that direction, by this guy is going to be in that direction. Okay. So then you'll see this component of the electric field and this component of this electric field, they are in the opposite direction, they will cancel. So the total electric field then will be the two components here adding up. Okay, so these two are then perpendicular to the sheet. Okay, so that's that. So then we know that E will be perpendicular to the surface. So again, I'm going to clean out this messy stuff here, and before we actually derive what will be the electric field here. Okay, so again, from the definition, flux is equal to, now again, three surfaces here. This time E is perpendicular to the bottom two surfaces. Okay, so then it will be E times the bottom surface area will be pi r squared, and then plus another one, E of pi r squared. Okay, okay. And the side surface, because E field is parallel to the side surface, so for the side surface, it's going to be having zero flux. Okay, so flux is 2 times pi r squared times E. Okay, according to definition of flux. Now, according to Gauss's law, flux will be equal to Q enclosed divided by epsilon naught. Q enclosed by this shape will be just this part of the surface. Okay, so it will be just surface charge times the area. Again, that part will be pi r squared. Okay, and divided by epsilon naught. Okay, so this is a flux according to Gauss's law. This is a flux according to definition. You're going to set those two equal to each other. Okay, so 2 pi r squared E is equal to pi r squared over epsilon naught. Okay, so the pi r squared will cancel. These two will go there. So at the end, you'll get E actually equals to just the oh, there's a sigma. I'm forgetting here. So sigma there, just equal to sigma divided by 2 epsilon naught. Okay, so that's the E field, and it's perpendicular to the surface. Okay, so you can see that actually the R cancels, so E field will be homogeneously parallel perpendicular to the surface. Okay, all right. So earlier when we talked about the um, parallel plate capacitor, right? I mentioned that um, according to the configuration, the capacitance will be just proportional to the area of the plate and then inversely proportional to the distance. Okay, so I did not offer the variation of that formula, but today we can take a look on that. Okay, but just keep in mind that what we learned in the last slide, that um, the E field by this guy, right? E field by this guy E by this guy is just epsilon over 2 times sigma 0. Okay, so then for parallel plate, if we have one plate, E field is going in this direction. Okay, in that direction, and E field by this plate only is sigma over 2 epsilon naught. Okay, now E field by this negative charge plate is going to be pointing towards that charge plate. Okay, so that and that. Okay, so it'll just be a different sign, but it should be epsilon divided by 2 times sigma divided by 2 epsilon naught. Okay, so these two will add up because they are pointing in the same direction, so you'll add them up. So then at the end you'll get sigma just over epsilon naught. For the electric field inside the two plate, outside the two plate will be each one have just 1/2 of that. Okay, so 1/2 outside, but inside is twice. Okay, in that case. So if we have E field inside that equals to this guy, okay, so then E equals to sigma over epsilon naught, which sigma is equal to the charge, right, divided by the area. Okay, divided by the area, and that will be sigma. You still have the epsilon naught there. The voltage across the two plate then will be E times D, okay, which is this times D, which will be Q D A epsilon naught. So according to the capacitance definition, C is equal to Q over V, So then we do Q over this whole thing, Q over this whole thing, over this QD, and divide by A over sigma. So those two will flip up, right? So it's A sigma there. So you can see Q and Q actually cancels, and you get that epsilon naught times A over D to be C, okay? So that's how actually the capacitance for the parallel plate capacitance can be derived, okay? All right, so we go back to the slide and then moving forward. Now, let's take a look on another example. In this case, we'll have actually um, three-dimensional charge distribution. Okay, so we look at the line, one-dimensional, surface, two-dimensional. Now, this case will be three-dimensional. Okay, so for three-dimensional, this is a sphere that have charge on it. So again, we can have a Gaussian surface, Gaussian spherical surface, concentric with this charge distribution. So then outside of the surface Gaussian surface here, electric field will be pointing again in the radial direction. If this is uniform charge distribution, then it's that would be the case. So then Q enclosed by the surface would be just the total, okay? Now, if we are looking for electric field inside that sphere, okay, so inside here, so you can draw another small spherical Gaussian surface, which is smaller than the original, then it will be just only part of the charge distribution that will be enclosed, okay? So then you only will have charge just in that smaller sphere, okay? So at point P outside the sphere, it turns out to be 1 over 4 pi epsilon naught Q total over R squared. If you apply the flux definition and then use Gauss's law to calculate the flux at the end, you'll get this result. If you are looking at the electric field inside the sphere, you'll get this result, okay? I'm going to switch here again and then show you guys how that can be done, okay? By looking at one example here. So here it says a sphere that is having radius of 6, and uniform charge distribution rho is given. So this guy is the uniform charge given. This will be the rho, and this is the radius of R in the sphere. So it's looking at two distance, R equal to this one is less than the sphere's radius. This guy is greater than that, okay? So let's say this is the 6 centimeter sphere, okay? This is terrible drawing, but imagine this is a sphere, okay? So R equal to 6, okay? R equal to 6 centimeter. So if we are looking at the inside the sphere here, this guy here first, so then we will draw a small kind of Gaussian surface, this small one here, okay, where this is small r, okay. So according to the flux definition, E field is going to be E times A because E will be in just in radial direction, which is means in that direction only, okay, E field. So it's parallel to the Gaussian surface of this spherical, okay. So it should be E times 4 pi R squared, okay. Now according to Gauss's law, that's equal to Q enclosed over epsilon naught, where Q will be just rho times the volume of this small Gaussian sphere should be 4 over 3 pi r to the third, okay? And then divide by epsilon naught. So these two should equal to each other. We'll set the E times 4 pi r squared equal to rho 4 over 3 pi r to the third over epsilon naught. And then there's cancellation here. We can work on 4 pi r squared will cancel 4 pi r to the q. The square will be canceled, and then you'll just leave with r here. So this will tell you E field is equal to just rho times r over 3 epsilon naught. Okay. Okay. And if we go back to the slide, so that would be something like this. Okay, so if you get Q enclosed, which will be 3 over 4 or 4 over 3 pi r squared r to the q, right? So the square and square will cancel, and then you're just left up with that. Okay, so that's the inside there. Okay, 3 rho times r over that. Now we can plug in the numbers here. So r is equal to 2 centimeters. Okay, so then we can say E field E is equal to 450 times 10 to the minus 9 times R. Even in this case, it would be 2 times 10 to the minus 2, okay, over 3 times 8.85 10 to the minus 12. Okay, so make sure you have everything in SI unit. So this will give you 339 newtons per meter of the electric field. Okay, on this one. But this one you can use as the when the inside the sphere. Okay, general expression for that. Now let's look at outside the sphere. So outside the sphere, then we'll draw a bigger Gaussian surface. Okay, so this one bigger than the original one, and then we'll use this. Okay, so the same thing. Flux will be equal to E times A. Again, be E times Gaussian spherical 4 pi r squared. All right. Just this case, r will be small r will be equal to 10 instead of equal to 2. Okay. This guy here, according to Gauss's law, again, you use that over epsilon naught. So then it'll be the Q total charge, okay, of here, because now it encloses the entire charge distribution there. So it will be Q total will be rho times V 4 over 3 pi radius of the sphere square, and then over epsilon naught. Okay, so again, you'll set these two equal to each other, and there will be cancellation of 4 pi and 4 and pi. Okay, but the r square and capital R to the q cannot cancel because they are different r's. Okay, so in that case, E is going to be equal to, with cancellations, you'll have rho times r to the third power over 3, okay, epsilon naught times r squared, okay. So this is the electric field when you are inside. Oh, this is outside, sorry, outside the sphere, okay. All right, and then we can plug in our numbers now for the electric field here. So E field equals to 450 10 to the minus 9. Again, make sure you have everything in SI units. Radius is 6 times 10 to the minus 2, and then you want to cubic that over 3 times 8.85 10 to the minus 12, and then 10 to the 10 times 10 to the minus 2, and this one to be squared. Okay, so this is a small r. So that will give you 366 newtons per meter for the electric field. Okay, so we do inside and outside, so differently there. All right, so let me see if I can capture everything just in a single screen here for you guys. All right, again, calculating flux use definition, and then use Gauss's law for when you are inside, and then the similar thing when you're outside. Okay, so we get two different expressions. E field is proportional to the radius when you're inside. It's inversely proportional to the radius squared when you're outside of the charge distribution here. Okay, all right. So, and we have gone through the solution there. So to summarize what we just look at, the example before that we just look at, if your inside is proportional to R, outside is inverse proportional to R squared. Okay, so this is what you see for uniformly charged distributions in three-dimensional. Okay. Finally, we'll just take a look at this one. Okay, so it says find an electric field due to a uniformly charged thin spherical shell of R and charge Q, total Q. So similar to the volume charge distribution, but this time because this is a shell, so inside is empty. Okay. So then when that's the case, when you are inside, flux is equal to E times A, right? And then that would be E times, again, 4 pi R squared. When you are inside, the shell. And according to Gauss's law, it would be Q enclosed over the epsilon 0, and that should be equal to 0 because inside here there's no charge, right? So then E field will be equal to 0. Okay, so combine these two, E field equal to 0 if you are inside. All right, and if you are outside, you can draw a spherical Gaussian surface like this. Okay, so then this will be similar to what we had just saw earlier. You will do again the two ways of calculating flux. So E times 4 pi R squared, and then flux then will be equal to the total Q over epsilon naught. Okay, so then combine these two, E field should be equal to just the total Q 4 pi epsilon naught times R squared. Okay, so 1 over 4 pi epsilon naught actually is K, so this will be then the same as KQ over R squared. Okay, on this one. All right. So then if you plot the E field versus the radius, so inside will be 0, and then outside, it starts with when small r equal to capital R, and then decay like that. It's just like a point charge. All right, so what we learned today is definition of electric flux, and then we also learned Gauss's law. So combine these two ways of calculating electric flux, we can find electric field by a line charge, a surface charge, or a volume charge distributions. Okay. All right, that will be it for today. We'll come back in another time. Okay, so see you guys next time.